Venus is often called a sister planet to Earth due to its similar size and rocky composition. However, the similarities end there. Its surface environment is extraordinarily hostile. The planet is shrouded in a thick atmosphere of carbon dioxide covered by dense clouds of sulfuric acid that reflect most sunlight, making Venus the third brightest object in Earth's sky, while completely hiding its surface from view. What secrets lie beneath this endless cloud cover? Surprisingly, beneath its glowing facade is a landscape shaped by volcanic activity and forces that remain only partially understood. Only recently have modern instruments begun peeling back these mysteries, revealing landscapes and phenomena more complex and active than anyone had imagined. Venus is no longer just an enigmatic neighbor of Earth, it's a planetary puzzle patiently awaiting its next discovery. It all began in the 1970s and 1980s as part of the Soviet Venera program. Spacecraft managed to withstand the planet's extreme conditions long enough to capture the first images of Venus's surface. In 1975, the landers Venera 9 and Venera 10 endured the crushing pressure and extreme heat just long enough to transmit the first photos from the planet's surface. Harsh black and white panoramas of a rocky plain. A few years later, in 1982, the Venera 13 and Venera 14 probes sent back the first color images of Venus's surface, revealing brownish rocks and soil beneath an orange sky. These pioneering landers revealed a landscape of fractured stones and flat slabs, strikingly similar to Earth's. Though they survived only about an hour before succumbing to the planet's hellish environment. Nonetheless, their cameras proved that landing and photographing Venus was possible, allowing humanity to glimpse this hidden world for the first time. While the Venera landers provided a ground-level view, a complete picture of the planet's terrain came from orbital radar mapping. In 1990, NASA's Magellan spacecraft entered orbit around Venus, and used synthetic aperture radar to systematically pierce through the planet's thick cloud cover. Over the course of 4 years, Magellan mapped approximately 98% of Venus's surface in high resolution. By bouncing radio waves off the surface, scientists were able to uncover astonishing details of its topography and geology. Towering volcanoes, vast basalt plains, winding rift valleys, and deformed highlands known as tesserae. Magellan's radar images reshaped our understanding of Venus, revealing a surface shaped by volcanism and tectonic deformations with relatively few impact craters. Furthermore, Magellan detected signs of extensive volcanic formations and even hinted that volcanic activity might not be dormant. Later, fluctuations in atmospheric sulfur dioxide levels led scientists to suspect that active eruptions could still be occurring. Since visible light cameras cannot see through Venus's perpetual cloud cover, scientists developed indirect imaging techniques to map and study the surface. One of the most powerful methods is radar imaging. Radar waves in the radio-microwave spectrum easily penetrate Venus's thick clouds and atmosphere. These waves bounce off the solid surface, then return to the spacecraft carrying information about reflectivity and elevation. Soviet orbiters, Venera 15 and Venera 16 first used this approach in the 1980s, mapping about a quarter of the planet's northern regions. Radar mapping revealed numerous geological details that optical instruments could never capture from orbit. Circular coronae formed by upwelling magma, long lava channels, mountain ridges, and impact craters. In essence, radar sees the texture and shape of Venus's surface, and that enables scientists to create 3D topographic maps and even assess surface roughness or composition. For example, high radar reflectivity at mountaintops suggests the presence of metal-rich frost. In short, radar became the key to unveiling Venus's hidden face. Another invaluable indirect method is infrared spectral imaging, particularly useful for studying Venus's night side. The dense atmosphere is mostly opaque to visible light, but there are a few narrow windows in the near-infrared spectrum. For instance, the ESA's Venus Express spacecraft, which operated from 2006 to 2014, carried an instrument called Veritus, Visible and Infrared Thermal Imaging Spectrometer. This device observed Venus in wavelengths around 1 micron, which can penetrate the lower atmospheric layers. From Venus's nighttime hemisphere, Veritus detected the faint glow of hot surface rocks. Venus Express used infrared emissivity maps to identify anomalous hotspots on volcanoes such as Mons. These hotspots had distinct spectral signatures indicating relatively unweathered and therefore fresh lava flows. In 2010, a study was conducted based on Veritus data. It yielded an exciting conclusion. Some of these lava flows could be geologically young, possibly just a few thousand years old. Practically yesterday in geological terms. This data provided some of the best evidence at the time that Venus is still volcanically active. This evidence was dramatically confirmed in 2023 when researchers reanalyzed Magellan's 30-year-old radar images and discovered an actual volcanic eruption captured in the early 1990s. They found that a volcanic vent on Mont Mons had visibly changed shape and enlarged between Magellan's mapping cycles, indicating an eruption and lava flow during those periods. This radar-based before and after comparison is the most direct proof yet of ongoing volcanism on Venus. The implications are profound. Active volcanoes could be releasing gases into the atmosphere even today. After the Magellan era, Venus exploration quieted down, but the 2010s and subsequent years have seen a revival with new technologies. One of the most unexpected contributions came from NASA's Parker Solar Probe designed to explore the Sun. During its gravity-assist flybys of Venus, scientists turned its cameras towards the planet. Surprisingly, Parker's Whisper imager managed to capture the first ever visible light images of Venus's surface from space, photographing its night side. The images revealed subtle bright and dark regions corresponding to continental highlands, plains, and plateaus, features visible only because the probe observed Venus's night side where its heat could be detected through the clouds. Around the same time, ESA's Bepi Colombo and the joint ESA-NASA Solar Orbiter made close flybys of Venus on their way to their primary targets. In October 2020, Bepi Colombo passed by Venus and captured stunning black and white images. Bepi Colombo's sensors observed Venus's magnetic and plasma surroundings and even detected oxygen and carbon atoms escaping from the upper atmosphere in a previously unexplored region of the magnetosphere. Similarly, the Solar Orbiter performed high-cadence plasma and magnetic field measurements on the planet's night side, offering insights into the induced magnetosphere created by the solar wind. In December 2015, Japan's Akatsuki spacecraft, known as Venus Climate Orbiter, finally entered Venus's orbit, carrying a set of specialized cameras to study the planet's dynamic atmosphere. Shortly after reaching orbit, Akatsuki's instruments detected a remarkable feature: a massive stationary bow-shaped cloud structure stretching almost from pole to pole over Aphrodite Terra. Additionally, Akatsuki observed winds similar to jet streams in the lower and middle cloud layers, discovering a fast equatorial jet that helps unravel the mystery of Venus's atmospheric superrotation. Different parts of the electromagnetic spectrum reveal different aspects of Venus, and these missions leverage this fact. In ultraviolet light, Venus's cloud tops display patterns of bright and dark shapes, including the famous large Y-shaped dark feature drifting around the equator. These patterns result from an unknown chemical absorber in the clouds that strongly absorbs UV radiation. In the near-infrared range, specific wavelengths become critically important. On Venus's night side, these windows allow thermal emissions from the surface and deep clouds to be detected. At slightly longer infrared wavelengths, we can see the silhouettes of lower and middle cloud layers, helping track cloud movements and detect changes in opacity or chemical composition. The thermal infrared range is useful for measuring cloud top temperatures and detecting thermal anomalies, revealing atmospheric waves and circulation patterns. Finally, at the far end of the spectrum, microwave and radio waves enable radar imaging and subsurface probing, allowing scientists to peer hundreds of yards below the surface. After decades of insufficient exploration of Venus, a new wave of missions is on the horizon. NASA has approved two ambitious missions, Da Vinci and Veritas, scheduled for launch in the late 2020s. Da Vinci, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is a combined flyby and atmospheric descent mission. The probe will directly measure atmospheric composition, searching for noble gases and chemical clues. As it nears the surface, the probe will capture the first high-resolution images of Venus since the Venera missions, focusing on Tessera terrain, heavily deformed highlands that may be analogous to Earth's continents. At around the same time, the powerful orbital mapper Veritas will conduct a global high-resolution surface survey. Its primary instrument is a state-of-the-art synthetic aperture radar system. Veritas will generate 3D topographic maps with far greater detail than ever before, detecting features as small as 15 to 30 yards compared to the 100-yard resolution of Magellan. Thanks to its interferometric synthetic aperture radar capabilities, Veritas will even be able to detect subtle changes in surface shape over time, such as volcanic inflating or fault line shifting. Following NASA's missions, ESA's Envision orbiter is set to arrive in the 2030s, equipped with a comprehensive suite of instruments to tie everything together. Uniquely, Envision includes a subsurface radar sounder, which will be used for the first time in Venus exploration, capable of probing up to a mile beneath the surface. Envision is essentially a synthesizing mission built on the legacy of Magellan, Venus Express, Akatsuki, Da Vinci, and Veritas to create a unified understanding of Venus. Today we stand on the verge of finally understanding why our sister planet, so similar in size and origin, took such a drastically different path, becoming a world with a furnace-like surface and an acidic sky. Perhaps these discoveries will one day help us prevent a similar fate for Earth. Or maybe they will reveal a way to reverse the process and make Venus into Earth 2.0,